Recommendations for electronic circuits prototyping. Use a 30-watt soldering iron to solder a component in Vero board. Use a soldering iron as sponge with water to clean the tip of the soldering iron. Use a good quality soldering wire to wire up your prototypes. Use a proper wire wrapping wire to wire up your prototypes. Use soldering fume extractor to protect yourself from the fumes of the soldering wire. Use a good quality tin-coated Vero board for your prototyping. Before writing our new program to read the analog inputs for PIC microcontroller, that is PIC16F877A that we are using in our prototype, it is better to understand the analog read concept, as we are using a microcontroller that is PIC16F877A microcontroller. Most of the PIC microcontrollers have a 10-bit successive approximation ADC converter. Some of the microcontrollers have 5 analog inputs and some have 8 analog inputs with them, and we can select the required analog channel using configuration registers. We can see from the datasheet that PIC16F877A microcontroller has a 10-bit ADC. After conversion of analog signal into digital number, the result is placed in two registers, that is ADC register high and ADC register low. Here we can find a 16-bit register which is divided into two registers, that is ADC register low and ADC register high. To read the value of any analog channel, that is from analog 0 to analog 7, we have two configuration registers, that is ADCON 0 and ADCON 1. And here we can see ADCON 0, it has 8 bits. 2 bits from ADCON 0, that is ADCS0 and ADCS1, with a combination of single bit from ADCON 1, that is ADCS2. All 3 bits are used to configure the clock conversion frequency. Here we can find if all these 3 bits are 0, then the conversion clock will be frequency of oscillation divided by 2. Similarly, we can find the different rates from this table. Here we can find 3 bits, that is channel select 0, channel select 1, channel select 2. These bits are required to configure the channel number which is required to read as analog input. Here we can see if all 3 bits will be 0, then the analog channel 0 will be selected. Similarly, we can see the combination of all 3 bits to select from analog channel 0 to analog channel 7. And here we have the second register, that is ADCON 1. By using the bits, that is PCFG0, PCFG1, PCFG2 and PCFG3, we can select that which pin will be configured as analog input or as digital input output. Here we can see different combinations of PCFG pins from 000 to 1111. From the schematic, we can see that we are using 4 analog inputs, that is analog 0, analog 1, analog 2 and analog 3. And we have interfaced 2 variable resistors with analog input 0 and analog input 1, that is variable resistor 1 and variable resistor 2. And we have 2 other analog inputs, that is feedback 1, which is coming from the PWM to analog conversion circuit. We'll learn about this circuit in our upcoming lectures. Similarly, we have another circuit which is PT100 amplifier. PT100 is a resistive temperature sensor, and we'll also discuss the circuit in our upcoming lectures. So here we have 2 circuits, that is PWM to analog conversion circuit and PT100 amplifier circuit, and here we have 2 analog input resistors. So we'll configure the bits of ADCON 1 accordingly. Here we can see from this table, if we'll select the value, that is 2, then we can have 5 analog inputs out of 8, and 3 of the analog inputs will behave as digital input output. Here we can see the table. So we'll assign the value, that is 2, to ADCON 1. And here we can see a block, that is frequency of oscillation divided by the number, that is n, and we can select this number from ADCON 0. If we'll configure these bits, that is ADC S0, ADC S1 and ADC S2 as 0, then the ADC clock conversion frequency will be frequency of oscillation divided by 2. Similarly, we can have different combinations as per configuration of these bits. Here we can see the most significant bit of ADCON 1, that is ADFM, and here we can see if ADFM will be 1, then the digital conversion result will be stored as write justified result, and if the value of ADFM will be 0, then the digital conversion result will be stored as left justified format in 16-bit register. As we are using MikroC compiler to program our prototype, MikroC compiler takes care of the ADCON 0 register. The command, that is variable integer ADC read channel, will automatically configure the bits to select the corresponding channel, and the result of ADC conversion will be stored in this variable. MikroC compiler selects the bit ADFM as 1 and stores the result in 16-bit variable as write justified format. If you would like to work with 10-bit ADC conversion, then we'll use the variable as it is. But if you would like to work with 8-bit ADC conversion, then we'll rotate write 16-bit variables by 2 times. In this way, we'll have the higher ADC register in lower byte of the variable, and we'll move the result in an 8-bit variable. In write justified format, the value of higher 6 bits of ADC register high will be 0. There is another consideration of TDA. 1 TDA equals to time for single bit conversion, and it must be greater than or equals to 1.6 microseconds. MikroC compiler itself takes care of this constraint, and the compiler automatically selects these bits configuration to meet the requirement of 1.6 microsecond for 1 TDA. How can we know that appropriate clock conversion value? And we can find this value from this formula, that is 1 TDA equals to Cc divided by frequency of oscillation, and it should be greater than 1.6 microsecond. As we are using 10 MHz crystal in our prototype, so we'll multiply this value, that is 10 MHz by 1.6 microsecond. So we'll get the value, that is 16. It means that the minimum value of clock conversion is 16. We can select a high value, but we cannot go below this value. According to datasheet, each conversion takes up to a minimum 12 TDA. Also, the oscillator value must be chosen as to produce at least a TDA of 1.6 microsecond. For example, it would take 19.2 microsecond for conversion to complete for frequency of oscillation divided by 16 if a 10 MHz crystal is used. So in our program, we'll assign the value 2 to Adc1 register. In our previous session, we have interfaced two variable registers with our prototype, that is variable register 1 and variable register 2 with pin number 2 and 3 of this microcontroller, and these pins are analog input 0 and analog input 1. Now we'll start writing our new project to read the analog inputs of microcontroller. So we'll go for the project, new project, standard project. Project name is ADC read. And the project folder will be, here we have a folder of ADC projects. So we'll select this folder, OK. Device name is PIC16F877A and the device clock is 10 MHz. OK, next, finish. Here we have our main program starting from void main. Now we'll add some comments and assignments to our program. Here we have assigned the name to our project, that is analog to digital conversion. As we'll display the value of ADC on this LCD, which is connected to port B of the microcontroller. So first we'll initialize the bits of this LCD in our program. And here we'll initialize the LCD bits. For this, we'll go to the help. In MikroC Pro for PIC libraries, we'll go for LCD library. And here we have LCD connection module. So we'll copy this module from this sample program. Control C, and we'll paste the connection details here, Control V. Now we'll go for MikroE libraries and we'll select system libraries, and here we'll select LCD libraries. Now we'll start writing our main program, and here we have our main program starting from void main, and in main program we'll write a while loop, that is while 1 and we'll write the while loop between these two braces. Before while loop, we'll assign the direction to the ports which we'll use in our program, and we'll also initialize the ports. So we'll write trace B equals to 0. Here we'll add comments. Port B is configured as output port, as we have interfaced the LCD with port B. Now we'll assign the value to the register, that is Adc1. So we'll write Adc1 equals to 02. In this case, we'll have 5 bits as analog inputs and 3 bits as digital input output. Here we will also assign the direction to the port A, that is trace A equals to FF, that is 255. It means that port A is configured as input port. So we'll add comments here. Here we'll write the LCD initialization module. For this, we'll go to help, and here we have module for LCD initialization, LCD clear, LCD cursor off. So we'll copy these modules from sample program and we'll paste these modules here, Control V. We'll also display some text messages on LCD display. So we'll write from the sample program, we'll copy these 2 lines, that is how to initialize the text messages. Control C, and here we will initialize the text messages. And we'll paste the text messages here, Control V, and we'll modify the text accordingly. So we'll write ADC channel 0 equals to and we'll also adjust the length of the message up to 20 characters. Here we will also modify the text to, that is ADC channel 1 equals to. Now before while loop, we'll print the text message 1 and text message 2 on LCD. We'll copy this command to print the text on LCD from sample program. Ctrl C, and we'll paste it here, Ctrl V, and we'll change the row and column accordingly. That is row 1 and column 1 and text 1. Now we'll copy this command once again, Ctrl C, and we'll paste it here, Ctrl V. Now we'll print the text message 2 on row 2. So we'll write row 2, column 1 and text 2, and here we'll change second row. Now in while loop, we'll call some subroutines, that is read ADC underscore R. Here we have a subroutine, that is read ADC value. As we'll read two ADC channels, so we'll assign two variables, and we'll assign the variables here. Variable assignments. Now we'll assign the variables, that is unsigned integer ADC underscore channel 0 equals to 0, unsigned integer ADC underscore channel 1 equals to 0. And now we'll write the subroutine, that is read ADC routine. So we'll write the subroutine before main program, and here we'll write void read underscore ADC underscore R, and we'll write the subroutine between these two braces. In this routine, we'll read two analog channels and we'll store the value in two variables, that is ADC channel 0 and ADC channel 1. So we'll write ADC channel 0, Ctrl C, Ctrl V equals to, again we'll go to the help, and here we can see the module, that is how to read the analog channel. So we'll copy this module from here, Ctrl C, and we'll paste it here, Ctrl V, and we'll replace this number by 0, as we'll move the value of analog channel 0 to this variable. So we'll change this number by 0. Again we'll copy this command to read analog channel 1, Ctrl C, and we'll paste it here, Ctrl V, and we'll change the name of this variable, that is ADC channel 1, and we'll also change this number, that is 1, as we are using ADC read module. So we'll select ADC library from system libraries. Here we can find an error in trace B assignment. So first we'll correct it, that is trace B. Trace B equals to 0. Now I'll call another subroutine, that is calculation routine. And we'll use this routine to divide this integer into unit, 10, 100 and 1000 digit. So we'll write the calculation routine before main program. And here we'll write void and we'll write the calculation routine between these two braces. Now we'll assign some new variables to display the value of ADC on LCD. Here we'll also assign comments, that is calculation routine, and here we'll assign some new variables, that is unsigned character unit underscore channel 0 equals to 0. Now we'll copy this assignment from here, Ctrl C, and we'll paste it here, Ctrl V, that is 10, a 10 place digit for LCD display, channel 0, Ctrl V, 100 place digit for channel 0, 100, and Control V, 1000 place digit, that is THU. Here we have defined 4 variables. Now I'll copy these variables from here, Control C, and we'll paste it here, and we'll configure these variables for channel 1. Now we'll use these variables in calculation routine, and here we'll write thousand place digit of channel 0 equals to ADC channel 0, Control C and Control V, divided by 1000, and we'll also adjust the decimal place, that is %10. Now I'll copy this line from here, Control C, and we'll paste it here, Control V, and we'll change this variable to 100 place digit, that is HUN, and we'll divide ADC channel 0 by 100. We'll copy this variable from here, Control C, and we'll paste it here, Control V, and we'll also modify this variable to 10 for channel 0, and we'll divide ADC channel 0 by 10. Control C and Control V, and we'll modify this variable accordingly, that is unit, and we'll modify this line accordingly. So here we have performed a calculation to place the digits of ADC channel 0 to their respective digit, that is 1000 place digit, 100 place digit, 10 place digit, and unit place digit. Now I'll copy all these 4 lines from here, Control C, and we'll paste it here, Control V, and we'll modify these lines for channel 1. Here we will replace this number by 1, and here we'll also replace by 1. So we have performed the same calculation for channel 1. Now we'll display these digits on line 1 and line 2 of the LCD. For this we'll call another subroutine, that is print routine. So here we'll write print_r, and we'll assign the comments, and we'll write the print routine before main program. And here we'll write print routine, that is void print_r, and we'll write the print routine between these 2 braces. From this text assignment we can check that where to place 1000 place digit, 100 place digit, 10 place digit, and unit place digit on LCD display. Here we can check column number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll write the 1000 place digit on column 10, 100 place digit on column 11, 10 place digit on column 12, and unit place digit on column 13. And here in print routine we'll write the characters on LCD display. For this we'll write LCD underscore character on row 1, column 10, and the number will be 1000 place digit of channel 0, Control C, Control V. To convert this number into equivalent ASCII number to print on LCD display, we'll add 48 with this number, plus 48. As we can see from the tools ASCII chart, here we can find to print 0, the equivalent ASCII number is 48, and we'll place this addition into 2 round brackets. We'll copy this command from here, Control C, and we'll paste it here, Control V. Now we'll change the column, that is 11, and we'll place the digit also, that is 100 place digit. We'll copy this line from here, Control C, and we'll paste it here, Control V, and we'll change the column, that is 12, and we'll change the digit also, that is 10. We'll paste the line once again, and we'll change the column, that is 13, and we'll change the number, that is unit. Now I'll copy all these 4 lines from here, that is Control C, and we'll paste these lines to print the value of channel 1 on LCD, and we'll modify these commands accordingly. Here we'll change the row 2, and here we'll change the channel 1. Now our print routine is ready to print the numbers on LCD display. Here we can check there is no error in our program and hex file is generated successfully. Now I will download the hex file to the microcontroller and will observe the result. Here I have selected the power supply jumper setting to power up the LCD display. Now I will connect PicKit3 programmer with prototype. Now I will start PicKit3 programmer software. I'll go to the file, import hex, and here we have ADC read hex file. OK. Hex file successfully imported. Right. Now we'll power up the prototype and we'll observe the result of our program. Here we can check ADC channel 0, the value is 0000. ADC channel 1, the value is 0000. Here we have variable register 1. If I'll change the voltages at pin number 2, that is analog channel 0, with the help of this variable resistor. Here we can check the value is changing. It will go up to 1023. Now we'll increase the voltages at pin number 3 of the microcontroller with the help of variable resistor 2. Here we can check the value is changing. It will also go up to 1023. Here we can check both channels are showing maximum value, that is 1023, corresponds to 5 volt. The voltages at pin number 2 and 3, that is analog channel 0 and analog channel 1, are 5 volt at this time. If the voltages at pin number 2 and 3 will be 0, the value of the channels will be 000. Here we have adjusted 0 volts on both channels, that is analog channel 0 and analog channel 1, and we can see the value is 000. So here in this session we have learned that how to read the analog channels and how to display the equivalent digital value on LCD display. In our next session we will learn that how to display the ADC value as 8-bit and how to convert this number into a meaningful information that corresponds to voltages, temperature, humidity, flow, or any other analog parameter.